All right, so carbon versus fluorine.
Carbon's bigger.
Carbon should be bigger. Same energy level.
Yeah.
Carbon has fewer protons. Carbon's bigger. Chlorine and bromine.
Bromine's bigger.
Same column. Bromine has more energy levels though. So we would expect bromine to be bigger than chlorine. Calcium 2 plus and sulfide 2 minus.
Sulfide.
Sulfide's bigger.
So we got to go through the process here and make sure, see if they're comparing the same number of electrons. Sulfide gaining 2 electrons makes it the same as argon, right? Calcium losing 2 electrons makes it the same as argon. Okay, so they both are going to have the same number of energy levels. They're both going to have the same electron configuration.
Different amount of protons.
It's just the amount of protons. 1s2, 2s2, 2p6, 3s2, 3p6. So if they're both, their valence shell's 3 for both of them, same number of electrons for both of them. Calcium's got more protons, which makes it smaller. Sulfide has fewer protons, so it doesn't pull them in as tightly. And then I was not even planning this, but the next ones also both have 18 electrons, right? These also are going to have the same electron configuration as calcium ion and sulfur ion, right? So again, same thing, we're comparing number of protons. We would expect potassium to be a little bit smaller because more protons pulling things in tighter. So argon would be larger. So it doesn't matter which way you get to it, just make sure that you're answering the question that was asked. It says what's larger, and then you go through your logic and say, well, therefore this one should be smaller. I'm going to pick that one. Make sure you answer the question that was asked. It says what's larger. So if your logic, when you're going through it, says, therefore this one's smaller, make sure you pick the opposite one, right? So just pay attention to what you're doing.
Just so I know that the negatives and anion and the positives of cation, what's the neutral? Just an ion?
Just atom.
Atom.
If it's neutral, it's not an ion at all.
Oh, okay.
So we just call it, it's just atom. All right, so then there's ionization energy, which again, went over in lab. But just to recap, this one is a graph that shows there we go. Get zoomed in. Most of what we care about for right now is right over here. Let's look at row 2. So starting with lithium, going to neon. In general, remember ionization energy is the energy to remove an electron. In general, the closer you get to having a full energy level, the harder it is to take away an electron. Because they don't want to give up electrons, they want to gain electrons to get to that full energy level, right? But on the lithium and boron and beryllium, they can give away electrons to get to only have their 1s orbital filled. Right, so in general, as you go left to right, you expect ionization energy to go up. It gets harder to take electrons away. And if this was the intro class, that's where we'd leave it. This isn't the intro class though, so we'll talk about a little sawtooth patterns that are in here. They show up in all of these. With these discontinuities, where it doesn't follow the trend, we can explain now. Jordan?
It's caused by having yeah, like half full orbitals.
Half full or full s orbitals.
Yeah.
Right, so beryllium versus boron. Beryllium has a full s orbital, boron has a full s orbital, and then one electron by itself. Well, it's easier to take away that one electron that's by itself. Anytime you've got an orbital that only has one electron in it, it's going to be really easy to take that one electron away. Because if you take that one electron away, now every orbital is filled. and it's an s orbital, it's filled, but it's, you know, it's still a filled orbital, even if it's not that big. So all of these examples, beryllium and boron, magnesium versus aluminum, correspond to a full s orbital versus a single electron in a p orbital.
Why is magnesium on the bottom? Beryllium's on the top. Or is that just, yeah. What?
So, sorry, no, that's not correct. This is magnesium.
Okay, cool.
That's aluminum. All right, so that all makes sense. These ones that are in the middle, though, so zinc versus gallium, that's a big drop, right? It's because, again, the gallium has just a single electron in a p orbital. Really easy to take that away. Versus zinc has a full d orbital and a full s orbital. It's a lot harder to take that first electron away because you have to break up a full orbital to take an electron away from zinc. But gallium has an electron all by its lone Z. One Z. Lone sum. Take your pick. Lone Z, I guess we'll go with. These ones in the middle, we can explain those too, though. Those are the ones that correspond to being exactly halfway filled. So nitrogen versus oxygen, they both have electrons in the 2p, right? So for nitrogen versus oxygen, nitrogen looks like this. And oxygen has one extra electron. So this is where the exactly half filled comes into play, right? In order to take an electron away from nitrogen, you have to break up an orbital that's exactly halfway filled. Now, half filled is not as good as all the way filled, but it's better than nothing. So breaking up something that's exactly halfway filled is harder than making something that's halfway filled. If you take away one electron from the oxygen, now it's more stable. So it's easier to take away one electron from an oxygen than to take one electron from a nitrogen because the nitrogen is exactly halfway filled already. And the oxygen will be exactly halfway filled if you take away that electron. Right? So all of these ones in the middle that don't follow our trend or barely follow our trend, these ones are almost the same. Those are the ones that correspond with an orbital being exactly halfway filled. And because the orbitals make things weird, gets a little funky in here because you have that ability to fill the orbital up exactly halfway at two different numbers of electrons. If you look right in the middle here, those irregularities for chromium versus vanadium. No, it's chromium versus manganese. So the d orbital does not follow it quite as cleanly when you're in the middle of the d orbital. But the p orbital, very, very reliably, and every time, it's always that 3p3 versus 3p4. Doesn't follow our trend because it follows these rules instead. Things that are exactly halfway filled are more stable than orbitals that are more than halfway filled.
And Sean, is it the same thing when you factor in, this graph doesn't go that far, when you do the F block as well?
Yeah, the F block even more so. Having an F block all the way filled versus having one extra electron, you see that discontinuity as well. And then you see this difference right here in the middle, that corresponds with the F block being exactly halfway filled as well. And so all the same rules, and in general, the bigger the orbital, the bigger deal it is to either be full, half, or empty, and nothing in between. Ideally, full is the best. If you can't have full, then it wants to be empty. If it can't have empty, it wants to be half.
Empty is essentially full, right?
Empty means that the level below is full, right?
Yeah.
So if you can get to, that's why all the metals are trying to give away electrons to get to only full orbitals from below by emptying their current valence. It's really full if you go down one energy level.
It's got oxygen in there.
This is same stuff we were just talking about. So for people that are following along on the slides, it's just more explanation of that.
So does a higher ionization energy mean it's more stable? It's the same thing.
Higher ionization energy means no. It means it's harder to take an electron away from. So fluorine's a really good example. Fluorine is really, really hard to take an electron away from, but it's not stable by any stretch, because instead of trying to take away an electron, fluorine gets more stable if it steals an electron from something else. So stable means that it doesn't want to change. A high ionization energy means it's hard to take an electron away, but it might have a very low electron affinity. Which I like to flip that a little bit. Electron affinity is how much energy does it give off when you give it an extra electron. Basically, how much does it want an extra electron? So electron affinity is basically the exact opposite of ionization energy. Ionization energy is how much energy does it take to remove an electron. Electron affinity is how much energy does it give off when you give it an electron. So fluorine has a very high ionization energy because it's really hard to take an electron away from it, and a very low electron affinity, meaning it really wants to grab an extra electron. But neon has a high ionization energy because it's already all full, but it also doesn't want to take an extra electron. So the noble gases will throw that off, that assumption off. Right, so the noble gases are what we consider stable because they have a high ionization energy and a high electron affinity. They don't want an extra electron, or they don't want to give up an electron. Neither one sounds good to them. I keep using, high in electron affinity is a weird one because they report the numbers as being negative numbers. That's the energy released when you give it an electron, which means it gets written as a negative. The more negative it is, the higher its electron affinity. It's a weird thing about switching your frame of reference with energy, right? Sometimes those negatives go away. So something that has a high, if you have an affinity for something, you like it, right? That's what affinity means. So fluorine has a really big electron affinity, which means it's really negative. Because that's the amount of energy that would be given away when you give it an extra electron. Yeah.
All of that for 1 electron to gain 1
To gain 1 electron, it will release 328 kilojoules per mole, which is a pretty big number.
Is that all it has?
Energy gets weird that
Not
way.
always.
Everything has energy, always. So it's not like it only has that much energy to give, because the mass itself is another form of energy. So it's
Free energy to get.
yeah. So that's once it gives away that 328 kilojoules per mole, fluorine is pretty stable. That's what fluoride is when you give fluorine an extra electron and turn it into fluorine with a -1 charge, and that's really stable, which means it doesn't have any free energy to give away. So I guess I would just rephrase the way you said that. Instead of saying that's all the energy it has, I would say this is its most stable state. In other words, it's going to be hard to get any more energy out of it. Does that kind of answer your question?
Yeah.
Okay.
It's the same kind of thing with electrons transferring from energy levels it gives out light, and that's a negative as well. It's the
Correct.
same.
Yeah.
The same. Essentially the same idea.
We're going to spend a fair bit of time talking about energy in this class, and in general, a negative energy change for the system means you're giving that energy away to the surroundings, either as light or as heat. So things that have a big, what are called exothermic reactions, like burning methane in oxygen. Take CO2 and H2O and a whole bunch of energy. We say delta H is the change in the energy for this reaction is going to be much less, much less than 0. So the chemicals are losing energy, and that in turn is being given to the surroundings. And that's exactly what we're seeing here as well, and that's exactly what we saw with the electrons going down in energy and turning it into light for the surroundings.
Negatives are coming from the system.
Exactly. We're always talking about from the point of view of the chemicals. So if the chemicals lost energy, the surroundings gained it. Right, and that's why these are negative. And it's greater than 0. You actually have to put energy in order to get neon to accept an electron. Basically, you have to force it. Neon really doesn't want to gain an electron. You can do it, but there's a reason they all just say greater than 0, because it's so hard we can't get a good number for it. We can't measure it reliably because it's so hard, and immediately it finds something else to give an electron to. So for all of these, it just says greater than 0 because it's really hard to force it to take an extra electron. And we see the same thing over here. These really don't want to accept an extra electron because giving these an extra electron means that they have a lone electron on the p orbital, right? So they're not super stable where they are, but if you put an extra electron, they really are unstable. Because the first thing they want to do is get rid of that one electron in the p orbital by itself. All right, so for the 5 of you that are in, you're all here, in lab from yesterday, we're not going to get to electronegativity before that assignment was due, so cross out electronegativity and replace it with electron affinity, which is just a different column, but it follows the same logic as what we were doing. So the reason there's always a chapter in every introductory chemistry book called periodic trends. Periodic trends just mean that things that we can relate to the periodic table where we can compare things. So that's what we've been doing this whole time. Atomic radius, ionic radius, ionization energy, electron affinity, those are all periodic trends because we can point to the periodic table and say, okay, as you go up and to the right, things get smaller. As you go down into the left, things get bigger. As you go up and to the right, ionization energy increases. And electron affinity increases up until you get to the noble gases anyway. And as you go down, size increases, ionization energy decreases, electron affinity decreases. So things get bigger, but it gets easier to take an electron away from them. And also, they also don't care as much about taking an extra electron. Their electron affinity also decreases. Fluorine would be even better at killing things than chlorine, but we don't use it in pools because it'd be too good at killing things.
Yeah.
And it reacts too quickly. So chlorine and bromine are sort of in the sweet spot. Iodine's not good enough at killing things. So we don't use iodine in pools or hot tubs. We use chlorine and bromine because they're in the sweet spot.
They use iodine for like parts baths.
They use iodine for parts baths. They use it for sterilizing your skin, partly because it's stable as a solution. These other ones are not as stable as a solution. So it's more about how can we package it properly in a way that has a shelf life. What's that? Like iodine tablets for backpacking. Those iodine tablets for backpacking are basically the same chemical that you use to sterilize pool water, except with iodine instead of bromine or chlorine. And we use bromine instead of chlorine in hot tubs because hot tubs are hotter, right? And so chlorine would be too reactive at that temperature, so we use bromine instead. Chlorine works in pools because the temperature is usually lower. And so you can keep it at a reasonable level. If you try to use bromine in a pool, it would be like trying to use iodine. It's not reactive enough.
Chlorine in a hot tub is way worse.
And if you use chlorine in a hot tub, you can shock it, you can kill everything in it, but it won't last very long. It's a little digression on water quality and halogens. There's one other trend that gets mentioned a lot that doesn't follow it's harder to predict, and it's harder to put a quantifiable number to it. And that's metallic character, metallicity. Things that are more metallic generally are going to have lowest ionization energies. So really, it's mostly based on that. And they're not the things you think of as being metals, actually. The most metallic elements are actually down over here. Sodium is actually more metallic than iron is because it has a lower ionization energy, which means it's malleable. Malleable comes from Latin malus, meaning hammer. Malleable means you can take it and you can pound it flat. Ductile means you can turn it into a wire by basically pulling two sides of it and stretching it out like taffy. And conductivity is both thermal conductivity and electrical conductivity. Things that are really metallic are really conductive, both thermally and electrically. So the most metallic elements, though, are over here. Normally we think of like copper and gold as being really metallic, right? They're not actually that metallic. They're just really good at not oxidizing. Things that are really, really good metals, you can't let them ever be exposed to oxygen or water because they oxidize. Their ionization energy is so low, they basically give those electrons away too easily, and they turn into something that's not conductive and not a metal anymore. Sodium metal is so soft, you can cut it with a butter knife. You can take your thumb in a glove and push it down, and you can actually flatten it. It's really interesting to touch and to work with, and we'll do a demonstration where we get some out and throw it in water and watch it explode.
Oh, sweet.
Yeah, it's one of my favorites. And it's really conductive because conductivity means those electrons are moving, right? Especially electrical conductivity. And so if it has low ionization energy, it's also going to be really conductive. Problem is we can't keep it as sodium metal in any sort of real world application. It's really good metal, but it reacts too easily. And that's why we actually use copper and gold in electrical wiring, because they don't oxidize at all. They're good enough conductors, and they don't react with oxygen readily, which means they last for a long time, even exposed to air.
So if let's say you ask us to compare two elements and which one's more metallic, let's say potassium and gold, do we go farther left is more metallic or farther down?
I will try not to ask you ones where you have to make that decision.
Okay.
And actually, I don't think on the midterm, I don't think I ask about metallic character at all. It's more that it's interesting to talk about, and it's something that I want you to be aware that it exists. But really, this matters more. This governs metallic character. Right? Low ionization energy means more metallic. So really treat it like you're looking at ionization energy. So potassium would be better than gold, generally speaking. Although we would want to, with it being two different aspects to it, we would want to double check that.
Okay.
When you go up to a high enough energy level, sometimes that matters more. Let's look at ionization energy. The lowest ionization energy should, in theory, be the most metallic, which would be cesium. All the way down here. And we just don't even have a number for francium, I don't think. I think this ends at the end of the sixth row. And this is what I mean about, so gold is down here, right? So sixth row, somewhere over here is gold. So if we're comparing gold to potassium, yeah, potassium is going to be more conductive, but not by that much. And gold is so much more stable when you expose it to oxygen. Gold makes a better choice.
The other thing, gold never tarnish.
Gold does not easily tarnish. You can make gold oxides, and in fact, that's what the smallest nanoparticles were, or the first nanoparticles were based on making gold oxides before they figured out how to make gold nanoparticles. You can get it to tarnish, but it's hard. And tarnish is just another way of saying oxidize or rust.
Yeah.
So silver tarnish is really just silver oxide that forms on the surface when silver reacts with the oxygen in the air. Interestingly enough, silver polish, you're not actually polishing it in the traditional sense that you're going to actually like rub off and remove the tarnish. Silver polish is actually tiny little pieces of zinc metal in a solution, it's an emulsion technically. But when you expose the zinc metal to the silver oxide, the zinc actually gives away its electron back to the silver, and the zinc then grabs the oxygen and turns into zinc oxide, which is soluble in water. So all you have to do, you're actually literally turning the silver tarnish back into silver metal. You're not just rubbing it off when you use proper silver polish. If you just take a sponge to it, you're just going to scrub it off. But if you use silver polish, what you're supposed to do, you're actually putting the silver back on it. And you can actually do that with, you can polish up copper that way too, by using silver polish, because it'll do the same thing with zinc. Interesting facts. But that's one of the reasons why silver lasts so long. Why you can have pieces of silver that have been cherished, that have been around since the Middle Ages. Because if you take care of it and you use silver polish, you can actually just keep those same atoms there, as opposed to just scrubbing them off year after year. All right, let's take a break, and when we come back, we're going to do some math. It's been a while, so we'll do some math for fun, not for fun. So we're getting ready for where we're going next. Let's come back at 5 till, and then we will get into talk about solids, liquids, and gases.
Midterm gonna be on Tuesday.
Sorry, thank you. Midterm is a week from Tuesday. I will give you the practice midterm this coming Tuesday.
3 weeks from this week.
Yes. So not 5 days from now, a week and 5 days from now.
Nice. My biology midterm is this coming Tuesday, and I'm stressed about studying with a.
Believe it or not, we generally do, I won't say we work together, but we try to avoid each other's tests. Sometimes that means that we stack them up on top of each other because we're all trying to avoid week 6. But not this time apparently for bio, so that's good. And actually a lot of math classes have midterms tomorrow, I think, or today, don't they? Or they already did. No, not for the rest of the day. Yeah, okay.
And Sean, for our midterms, we get our periodic table and a conversion sheet, right?
Yep, the same conversion sheet, equation sheet, and periodic table we've been working with, hopefully.
But not ours, right?
Not the one you've been taking notes on. I'll give you a fresh copy.
Oh, shit. Okay.
But having taken notes on yours will still help, because when you look at a blank one, you're gonna say, oh, normally I have a circle there. Why was that? Oh, yeah. Like, it'll help trigger and help you remember things, even if I do take away that a little bit.
Can we take notes on that copy?
The one fresh one I give you?
Yeah.
The first thing you do when I hand out a test is go to the periodic table and mark it up so it looks like the one you have to study from. That's fine.
Perfect. And our calculator as well.
Calculator as well.
Are there any like formulas or things that we need to memorize that won't be on the conversion sheet?
If you think you come across one, let me know, because either I missed it and if I miss anything that should be on the conversion sheet, like occasionally, I realize, I didn't give you a conversion for, ounces to something weird that we don't use a lot, then I'll write that conversion on the board. And so it's not a test about memorizing now that you've memorized your elements and symbols. Now it's about knowing how to use what you have.
What kind of calculator can you use?
The kind that you have.
Yeah, I've been using Wolfram Alpha.
So you won't be able to use Wolfram Alpha, but you can use your phone calculator. You just have to put it in airplane mode.
Okay.
So whatever, I would get comfortable using whatever calculator you have, and I'll bring some TI-83s for people who have been using the ones in lab. Mark?
I have just like a normal like TI-34, like a scientific one. That's fine.
That should be fine, yeah. Just use what you know how to use.
Something like that.
All right, when we get into stuff like pH and logs, then it can wind up, it's harder to use some of those, but they still have everything you need. It's about knowing how to use what you have. And in theory, you could get close to an A. I think you probably actually get an A on the midterm without using a calculator at all. If you show your work and just don't have a calculator and to hit enter, you can still show your conversions, right? You can still show how many sig figs there should be and things like that. And so when you hitting enter is a 1 point out of 10. 9 out of 10 points on conversions and things are did you set it up right? So in theory, you could go without a calculator, do all the work, turn it in, and probably get somewhere between an 85 and a 95 if you did everything perfectly, but never hit enter on your calculator.
So you kind of be grading these how you grade our quizzes, like even if you don't get the right answer, as long as you
Partial credit. Show me what you know. The test is not designed for me to trick you. The test is designed so that you can show me what you've learned so far. Right? So approach it that way, not I need to get to the right answer. I know almost all the way how to solve this problem. So show me the parts you do know. It'll be on paper. I'll have printed copies of everything. It'll be a thick stack of paper because I try to make sure that you don't have a ton of it'll be 10 parts. Here, while you guys are thinking about this, and as we're all coming back here, let me just pull up the practice so you can see what we're looking at.
And we're going to get the same exact practice, like a couple
Yeah,
days before
the practice is there it is going to be a version of 2019's midterm. 2019 because last year was different. I had to write tests differently. Where's it? Hang on one second.